Hey there, folks. So, about 2 weeks ago or so, I was engaged in a conversation on Twitter, naturally, and me and this individual were having a discussion about something called quantum realism. And he shared an article to me from Physics World, which is the magazine through the Institute of Physics, which is very, very reputed. It's headquartered out of the United Kingdom. And I have to be honest, I wasn't very pleased with how this article worded a lot of things, and I can certainly tell that it contributed to his misunderstanding. So we're going to dive right in here and take a look at this article and explain why it's not a very well put together article in terms of what it's saying, and why it's leading to people like this individual here misrepresenting what the science says. So the title right off the bat, Quantum Physics Says Goodbye to Reality. I don't really have many qualms with this, simply because we're talking about quantum realism, and somebody that this could be interpreted in a number of ways, so I'm really not going to make a big deal about that. I do think that in some sense it's kind of playing to an idea that reality isn't actually real if we're not looking at it, which is, I'm sure some of you have probably already guessed, a large part of what this article says. So right here, the little summary of the article. Some physicists are uncomfortable with the idea that all individual quantum events are innately random. I think stochastic is a better word to use than random, but that's just me. They essentially mean the same thing, but the term stochastic or stochasticity has slight differences, nuances in its connotation rather than random. I think it's more applicable to the realm of physics. But again, that's just me. This is why many have proposed more complete theories, which suggest that events are at least partially governed by extra quote-unquote hidden variables. Now, physicists from Austria claim to have performed an experiment that rules out a broad class of hidden variable theories that focus on realism, giving the uneasy consequence that reality does not exist when we are not observing it. That's what, and I think I was able to actually find the paper published in Nature. Of course, naturally, I could only find the abstract because Nature has paywalls. But this last phrase here, giving the uneasy consequence that reality does not exist and we are not observing it, I'm not a theoretical physicist or a quantum physicist myself, but I've spent just over a decade involved in research. I've read textbooks on the subject. I've watched lectures on it through MIT OpenCourseWare and through Stanford. I have a fair understanding of it. I'm not going to claim that I'm a professional or anything, but from what I understand and from what I've asked other people, that this sentence here is just not accurate. This is not, and we'll get to why, but I don't want to get ahead of ourselves. But this is just not a good way to talk about realism as it pertains, not just specifically to quantum mechanics, but just physics in general. Realism realism means something different than what most people would think it means, say, if you were speaking of like philosophical realism. And I'm not going to read these first couple of paragraphs because they just talk about Bell's inequality and Bell's theorem. And for those that don't know, Bell's inequality states that, well, if we have two entangled particles, it seems that they can affect each other instantaneously even if they're separated by vast distances, which seems to violate physics because information can't travel faster than the speed of light. But maybe there are hidden variables, or what's often referred to as local hidden variables there, that are giving the information to these photons or electrons or what have you that are entangled. So what if we can change, say, the thing that we're measuring after that particle has left whatever source has emitted it? And if these hidden variables did exist, they wouldn't be able to know that the orientation of this machine or the way in which we're measuring the particle that was emitted from it has been changed. Generally, it's orientation. You're measuring it along a different axis. That gets into some of the aspects of the vector spaces that are involved with often referred to as like measurement spaces that are involved, eigenspaces with measuring things, quantum mechanics. But if you measure it along a different axis, you can get entirely different measurements. And then if you go back to the axis you previously measured it on, you can get a different measurement or a different number than what you got the first time. Anyway, if there were hidden variables, they wouldn't be able to know that you were measuring it along a different axis after the particle had already been emitted from whatever source. And I think that's what it's saying right here. Bell's trick, therefore, was to decide how to orient the polarizers only after the photons left the source. If hidden variables did exist, they would be unable to know the orientation. I wasn't trying to look that up. And so the results would only be correlated half the time. On the other hand, if quantum mechanics was right, the results would be much more correlated. In other words, Bell's inequality would be violated. And what we find is that in entanglement, the majority of the time, you will get a weighted set for measurements for both particles, or measurements for another particle if you measure one, that directly correlate to the measurements of the particle, or to the measurements you made on the one that you did measure. Not all of the time, but 3/4 of the time or more. It's a 70-75% chance or more. And so what this does is, right here, on the other hand, if quantum mechanics was right, the results would be much more correlated. In other words, Bell's inequality would be violated, and that's exactly what we observed. The results were correlated significantly more than half the time, indicating that there has to be something more than simply hidden variables, and it's just that the system is described by the same wave function. In entanglement, it's not that there's actually any information traveling at or faster than the speed of light. It's just that the system that you're describing, all the aspects or particular components of the, like if you've got two entangled particles, both particles are a part of the same system, and the whole system is described by the same wave function, such that if you know what's going on with one particle, if you know what's going on with one aspect of the system, you'll know what's going on with the other, or at least you'll get a weighted set that will be strongly correlated to the measurements you make on whatever particle it is that you measure. So that was one thing I wanted to show. I also, really quickly, because Bell's inequality often brings it up, because this was taken a step further with what's been called the delayed choice quantum eraser experiment, which some people that I'm not going to name here, I've tried to argue that it supports something along the lines of, you know, retro causality or something like that, and it doesn't. All it shows is that when a particle goes to a double slit, its wave function, and this includes anything that its wave function may be entangled with, will innately evolve through both slits, but there are ways that you can affect it where you only get information about what went through one of the slits, or you might be able to get information about what went through both slits. And depending on which one you're getting information about, it can look, the measurements can change such that it appears as if this particle went back in time and changed its decision, but that's not what happens. And I have here from Preposterous Universe, which is Sean Carroll, who's a well-respected and very well-known theoretical physicist. This is his personal blog. This paragraph here is the one that I wanted to quote you guys. Quote, after a short befuddled pause, the class erupts with objections. Decisions? Backward in time? What are we talking about? The electron doesn't make a choice to travel through one slit or the other. Its wave function, and that of whatever it's entangled with, evolves according to the Schrödinger equation, just like always. The electron doesn't make choices. It unambiguously goes through both slits, but it becomes entangled along the way. By measuring the recording photons along different directions, again, that goes back to orientation of measurement and their vector space, that's a different video, we can pick out different parts of the entangled wave function, some of which exhibit interference and others do not. Nothing really went backwards in time. It's kind of a cool result, but it's not like we're building a frickin' time machine here. So I just wanted to mention that really quickly for those that would try to bring up something like that. Down here is where we get into the interesting part. Many realizations of the thought experiment have indeed verified the violation of Bell's inequality. These have ruled out all hidden variable theories, at least local hidden variable theories I should specify, based on joint assumptions of realism, meaning that reality exists when we are not observing it, and locality, meaning that separated events cannot influence one another instantaneously. But a violation of Bell's inequality does not tell specifically which assumption, realism, locality, or both, is discordant with quantum mechanics. This realism, reality exists when we are not observing it, that's not what realism means in physics. That's more along the lines of what realism means in philosophy, that if there isn't a conscious observer of it, then the thing doesn't really have any definable ontology. It doesn't really exist. And this is something that you might find in, like, say, idealism. Did I just mention that? Did I mention idealism? I think I did. Something like idealism, yeah. You know, reality is reality really there if we're not there to observe it? Is there really an ontology that's present? Most idealists would say no, at least nothing physical is, that mind is what's fundamental to reality, and so you need a mind in order to create physical reality because there has to be something there observing it. And this really is why this article would be cited by a theist, which is who I was engaged with. Continuing, Marcus Ospelmayer, Anton Zeilinger, and colleagues from the University of Vienna, however, have now shown that realism is more of a problem than locality in the quantum world. They devised an experiment that violates a different inequality proposed by physicist Anthony Leggett in 2003 that relies only on realism and relaxes the reliance on locality. To do this, rather than taking measurements along just one plane of polarization, the Austrian team took measurements in additional perpendicular planes to check for elliptical polarization. So the Leggett-Garg inequality is an interesting inequality. I don't know exactly what it says, but there is a Wikipedia page here that I had pulled up. I know that with realism, what it says about realism, and we'll get here, but I know what it says about realism is true, but the way that a lot of people interpret realism is not exactly what realism actually is. So just continuing here, they found that just as in the realizations of Bell's thought experiment, Leggett's inequality is violated, thus stressing the quantum mechanical assertion that reality does not exist when we're not observing it. And again, that's not a quantum mechanical assertion. Quantum mechanics says nothing of this. Nothing in physics says anything like that at all. This is why this is bad science communication. They're and it's not that I don't think the person knows that that's not what it says. It's more that I think the person is oversimplifying it for a lay audience, such that it's miscommunicating what is actually being said. And that's why I've started this particular series, Bad Science Communication, because articles like this, I think, need to be called out. This is not the proper way to be communicating the concept that you're trying to communicate. Our study shows that just giving up the concept of locality would not be enough to obtain a more complete description of quantum mechanics. Ospelmayer told Physics Web, you would also have to give up certain intuitive features of realism. However, Alan Aspect, a physicist who performed the first Bell-type experiment in the 1980s, thinks that the team's philosophical conclusions are subjective. I would agree. There are other types of non-local models that are not addressed by either Leggett's inequalities or the other experiment, he said, but I rather share the view that such debates and accompanying experiments such as those by the Austrian team allow us to look deeper in the mysteries of quantum mechanics. So, with that all of that in mind, let's look at what realism really is in physics. So, this is the Wikipedia page. So you can take it for what it's worth, but obviously, as you can see here, it cites its sources. The Leggett-Garg inequality, named for Anthony James Leggett and Anupam Garg, is a mathematical inequality fulfilled by all macro-realistic physical theories. Here, macro-realism, macroscopic realism, is a classical worldview defined by the conjunction of two postulates. And this is, again, according to their own paper, is explaining this. The first postulate, macro-realism per se, a macroscopic object which has available to it two or more macroscopically distinct states, is, at any given time, in a definite one of those states. So say, if you had a coin, that coin is either 100% on heads or 100% on tails. There is no in-between. It is only one or the other. The second postulate, non-invasive measurability, it is possible, in principle, to determine which of these states the system is in without any effect on the state itself or on the subsequent system dynamics. So what this is saying is that if you wanted to measure that coin and figure out which side it's on, heads or tails, measuring the coin isn't going to change anything about the coin or the way that it exists or evolves. And both of these are very much true for the classical level of reality. But what the Leggett-Garg inequality, or rather the violations of it, shows is that with quantum mechanical states, number one, there are certain properties such as position and momentum, energy and time, even things like spin, which do not have distinct states at any given time. The states are not distinct until you interact with the system. And the second one is also violated, where interacting with a quantum system can affect the system and its dynamics. So both of these are false. The idea, like what this paper seems to be indicating, that there isn't any sort of ontology to physical reality or to quantum mechanics independent of measurement, is not at all what is being said. That's not what realism is in physics, and the violation of realism does not mean there isn't actually a reality independent of measurement. What it's saying is that there aren't definite states to these physical systems independent of measurement, and that when we measure these states, it could potentially change what the states are doing. But it is not stating that there are no states there. So this is just, I'm sorry, but this article just does not accurately portray the idea of realism, nor does it really portray what the violations of Leggett's inequality are telling us. And that's why I needed to make this video. This is bad science communication, in my opinion. And it's stuff like this that I'm going to be talking more about. It's stuff like this that I'm going to be going over. Because, number one, it doesn't do the actual science justice. I think that I've explained both what realism are and what the violation of it is, what it actually means in physics in a way that most lay people could probably understand, at least I hope. So it's not like that the explanation that's given here can't be done better. It's just that this John Cartwright, I guess, who's actually, I think, Physics Web. I don't know if that's associated with the Institute of Physics or not, but this is from April 2007, naturally, so that may have something to do with it. This is a 14-year-old article. Not that the information in it is like wrong or inaccurate or outdated. I wouldn't say that, but it's just I don't think it's communicated very well. So make sure that you guys are keeping an eye on things like this. Make sure that you guys are keeping an eye on when people are sharing articles that don't really communicate these ideas very well. And make sure that you call it out, as I have, and I will continue to do. And with that, I'll leave you guys with per clausum nos perfectum, or through reason we progress.